physics, what we had started was that I talked about enthalpy change of atomization. Okay, what was enthalpy change of atomization? Okay, you're supposed to form 1 mole of atoms from the element, right? So it had to be 1 mole of gaseous atoms. You would break bonds, which is why it was always endothermic. And I explained that sometimes you can find it using bond energies, but bond energies are only applicable if the molecules are gaseous. You can't do that for atomization of carbon. You can't use bond energies for that because in that case, the element is a solid. So bond energies are not defined for solid elements. So electron affinity, this was what we were doing. Electron affinity was the energy that is released or absorbed when an atom basically gains an electron, a gaseous atom. And I told you that the first electron is usually gained by itself. It's able to attract that electron. It's a neutral atom. Its nucleus is going to pull the electron. So all the work done is going to be by the atom itself, which is why the first electron affinity is going to be exothermic. You don't have to do anything. But the second electron affinity, when it's an ion, gaining an electron becomes very difficult because now they're both negatively charged. There's going to be repulsion. So you have to give them energy so that they can overcome the force of repulsion. This electron has to be given some kinetic energy. So it's able to move towards the ion and overcome the repulsion. So the first electron affinity is always exothermic. The rest are all endothermic. And it's going to become increasingly difficult for it to gain electrons because every time it gains electrons, it becomes more negatively charged. So it's going to repel the electrons even more, which is why gaining electrons subsequently becomes more and more difficult. Okay? So is that part clear? This one?
Yes.
Yes.
So now, there's a thing called, I mean, we're going to discuss electron affinities in group 17, whether it's going to become more difficult to gain electrons or one second, let me move this, or it's going to become less difficult to gain electrons down the group. So I've got fluorine and chlorine and bromine, and we're talking about the first electron affinity, which is going to be exothermic because all the work is going to be done by the atom itself. So what do you think, Amit, what do you think would happen over here? Would it become more exothermic or less exothermic down the group? Do atoms like to gain electrons down the group? इनमें से किस एटम की attraction ज्यादा होगी, फ्लोरीन और iodine? Which one really likes to gain electrons?
Fluorine.
ठीक है, fluorine is, smaller atoms are more electronegative, right? So smaller atoms are more electronegative, while the lower the atoms down the below, they've got more shells, and the size increases, so they tend to be less electronegative. So fluorine is going to do the most work to gain electrons. It's going to attract electrons very, 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 very strongly. So if I plot electron affinities of fluorine, chlorine, bromine, and iodine is the least. It doesn't really like to gain electrons. It's got too many shells. It's not going to attract electrons very strongly, so it's not going to do a lot of work. So iodine is going to be the least exothermic. तो ये मैं plot कर रहा हूँ यहाँ पे कि so iodine happens to be the least. I mean, let's say this is iodine. Here's this one is iodine. Then you have bromine, as in not the diatomic iodine, just the atom. Then I've got bromine. That would be slightly more interested in electrons because it's a smaller atoms, fewer shells, less shielding. So it's going to do some work to gain electrons. Then I've got Cl. So Cl is an even smaller atom, so it's going to attract the electrons more strongly. So it's going to be even more. It's going to be even more exothermic. Just one second. And then you have finally you've got fluorine. Now fluorine is actually an exception. Fluorine actually does not really like to do a lot of work to gain electrons. Its electron affinity is actually it's not. I mean, the rest of them are following a pattern, and the reason for that is that the atoms they become more shielded, and they are less attracted to electrons. So electron affinity is less exothermic. Okay, this is electron affinity. So fluorine is an exception. Fluorine does not follow the trend. Okay, it does not follow the trend. It should be gaining electrons very, very strongly, attracting electrons, doing a lot of work to attract electrons, but it doesn't do that. It's not interested in electrons or gaining electrons that strongly. And there's a reason for that. And the reason simply is that the fluorine atom is actually too small that, and it's got too many lone pairs. I mean, the others have lone pairs as well, but because the size becomes too small, that an electron that's being gained from outside would actually face a lot of repulsion because the electrons are like too concentrated now. So it actually becomes harder to actually gain electrons. If it had been a bigger atom like chlorine, it would not be the case. But in the case of fluorine, the lone pair charge density is extremely high. So high charge density lone pairs, because they're so crowded together because of the small size, they repel electrons from outside. So it becomes harder or more difficult to gain electrons. So that's why fluorine is an exception. And the same trend kind of repeats in group. It's kind of repeating in group 16 and 15 as well. In 16, it's oxygen. Oxygen is not that because of the lone pairs being so crowded together that it doesn't really like to gain electrons very, very strongly. Ye clear? Is this thing clear? It's all clear, Saif, is this clear? Umayyad, clear?
Yeah, yes, sir.
Yes, sir.
Okay, so that's it. That's all about electron affinities, right? Uh, the tendency for an atom to actually gain electron. That's it. The next one, the next definition. Now that's an important definition. And using that definition, we can also construct bond-neighbor cycles. Now the last one. Now this is the important one. That's lattice energy. Or also written as delta H LE, not standard lattice energy. So what really is lattice energy? Now, lattice energy is basically you're forming, and it's specific to ionic compounds. It doesn't apply to any covalent or any other solid lattices. So it's specific to ionic lattices only. It doesn't really make sense for any other compound. So the definition simply is that you're forming 1 mole of solid ionic lattice that needs to be formed. So for example, if I'm making NgCl2, solid. That's 1 mole of solid ionic lattice. And I'm going to make it from its ions. So 1 mole of solid ionic lattice needs to be formed from its ions. The ions are Mg ions and 2 Cl ions. I need 2 Cl ions, I need 1 Mg ions, and I need them in the gaseous state. That means they're like flying around and they join together to form ionic compounds. So if you want to picture this, it's going to look something like this, that you have these positive and negative ions that are independently floating around. तो इसको copy कर लेते हैं, ठीक है? So let's say there's a positive ion, and they are independent of each other. I mean, they've got nothing to do with each other, so they're just for a second. एक second. So I've got positive ions, negative ions, positive ions, negative ions, positive ions, and they're all flying around in gaseous state. They're not bonded to each other. They're all independent. And if they're put together, they would attract each other and they would form a lattice. So the lattice would, they'll all get together to form this ionic lattice. Ionic lattices, they always look like this. Let me put together an ionic lattice. One second. Okay, so positive ions are attracted to negative ions. So that's what the ionic lattice looks like. It's all positive and negative ions joined together. Okay, so positive, negative, positive, negative, negative, positive, always alternating ions. So this has to be, you're forming 1 mole of ionic lattice from its constituent gaseous ion. So all that has happened in this, a crystal has been formed and bond formation has happened. Specifically, ionic bond formation has happened. Hence, your lattice energy is exothermic. So this thing over here is going to be exothermic. Lattice energy is always negative. So is the idea clear what lattice energy is?
Yes. Yes.
So I'm just going to write a proper definition for this. That's it. So the proper definition for lattice energy is that it's the energy that is released. I mean, they're going to ask for this. This one is important. Energy released when what happens when 1 mole of solid ionic lattice is formed. Is formed from what? From its constituent gaseous ions. And measured under standard conditions. And that's it. So So for example, the lattice energy of aluminum oxide, other examples would be that the lattice energy of aluminum oxide would be that aluminum ions gaseous and oxide ions, which are also gaseous, they get together to form 1 mole of ionic lattice, which is Al2O3 solid. So you have to balance it accordingly. The product should be 1 mole. So there should be 3 oxygen ions and 2 aluminum ions. So the enthalpy change for this reaction is going to be known as the lattice energy of aluminum oxide. Similarly, if you've got sodium oxide, so you want to form 1 mole of sodium oxide solid ionic lattice from what? From its constituent gaseous ions. The gaseous ions will be what? Sodium ions and oxide ions. And there's going to be 2 sodium ions. So the lattice, so the energy for this reaction is going to be known as the lattice energy of sodium oxide. So basically, it's the energy that is released when these ionic bonds they get formed. Okay, so it's clear as सब कुछ? Is this clear?
Yes, sir.
Yes, sir.
अच्छा, अब इसमें ये कि if you have a stronger lattice getting formed, then the amount of energy that's going to be released is going to be more exothermic. It's going to produce a lot more work. If you're forming a weak lattice, then it's not going to be that exothermic. So it depends, the size of the lattice energy depends on the strength of the ionic lattice. So stronger lattices, that means, so that means more exothermic lattice energy, and vice versa. If you've got a weaker ionic lattice, then it's not going to be that exothermic, so less exothermic. It will still be exothermic, energy is going to be released, but it's going to be considerably less exothermic. Now, examples of ionic lattices around you. I mean, a weak, अच्छा कोई example दे दे. What's a weak ionic lattice? Do you have an example, like in your home, of an ionic compound that's a weak lattice?
NaCl.
Because NaCl is a weak lattice. You can just crush it in your hands. It's a crystal like this. You put it in water and you stir vigorously, and the ions they all scatter in water. I mean, the lattice quickly dissolves. That's basically what's happening. The lattice disintegrates when you try to dissolve it. Even in your hands, you can just crush it very, 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 very easily. So NaCl is like a very
I'm sorry. I'm
yeah.
sorry.
I couldn't hear you. Can you repeat? Saf, what happened? So one example is NaCl, right? Achha, so just 1 second. Achha, what about a very strong lattice? Again, give me an example that's yeah, basically just give me an example of a strong ionic lattice or an extremely strong ionic lattice. I mean, there's an example in your home as well. I mean, there's probably a very strong ionic lattice, like right where you're sitting. Okay, कोई idea? Ahmed, Saad, Ahmed, is any idea?
Not sure, sir.
So weak lattice is NaCl, right? I mean, you know it's a weak lattice. It just disintegrates, dissolves. You can crush it in your hands, right? So you've got a strong lattice as well. Take for example, marble is a very strong lattice. It's calcium carbonate. Marble. Your concrete is kind of like an ionic compound as well. It's got a component that's ionic. Cement, etc. That's kind of ionic because it's got it's got calcium ions and carbonate ions, and they're all attracted to each other. There are some that are extremely strong ionic lattices, like magnesium oxide and aluminum oxide, which are known as ceramics as well. Magnesium oxide is I mean, you make heat shields. I mean, it's like bricks. It's a marble hota na, magnesium oxide is like very similar to it. So I mean, they're bricks. Shuttle ki jo bottom part, the bottom part of the space shuttle, which is black, that's basically bricks that are made out of magnesium oxide, or tiles that are made out of magnesium oxide. It's very strong. Similarly, aluminum oxide, most of your heavy transmission lines, high voltage transmission lines, the devices that you see, if you see a high voltage transmission line, they are devices that are gripping the wires. So those devices, because it's high voltage, anything that is weak, that's got a weak structure, would break down very easily. So you use aluminum oxide for that. So that's used for high voltage transmission. ठीक है, जो electricity poles के ऊपर ना, you see these things that are grabbing onto the wire. Even the transformers, the body of the transformer, that's kind of made out of a ceramic material as well, like aluminum oxide. So anyways, there are things that are very strong ionic lattices. I said, now moving to the more important question. How do you predict, or what are the factors that would determine whether a lattice is strong or weak, an ionic lattice? क्या होगा? Why is NaCl weak? Why is calcium carbonate strong? What's the reason for that? Or why is magnesium oxide so strong?
Sir, it dissociates more in a solution.
ठीक है, we know that marble जो है ना, it's marble does not dissociate. Marble, the ions are like very strongly attracted to each other. Like even if you wash it, nothing happens to it. The ions are still sticking together. So that's what I'm saying. What are the factors? Like, why is calcium carbonate stronger than NaCl? Well, the factors क्या होंगे? Why is NaCl
Sir,
weak?
is it the charge on the positive cations?
ठीक है, positive and negative ions, right? It's basically, what's an ionic bond? Ionic bond is basically the attraction between a positive ion and a negative ion. So if you have larger charge, ठीक है, so factors that determine determining strength of the ionic lattice. So the number one factor is the charge. So the charge on ions. You've got lesser charge like NaCl, then obviously there's not going to be a lot of attraction. You've got more charge, like you double the charge, then the attraction doubles as well. So this is weak, while this one is strong. Achha, any other factor apart from charge? क्या होगा?
Sir, the size of the lattice, maybe.
The size of the ions. Because if you have smaller ions, they would tend to be more tightly packed together, and since they would be closer to each other, they would because of the closeness, the attraction is going to be stronger. Bigger ions would be further away from each other, so because they would be too far away, they wouldn't be really attracting each other that strongly. So the second factor is the size of the ions. So the second factor is size of ions. So together, both these factors can be referred to as charge density. Charge density is basically the charge on the ion versus the size of the ions, or ionic radius. So So I'm just going to practice a few questions because they're going to ask you for the reasons for which, I mean, they're going to do some comparisons. So can you tell me which of these compounds are going to have a more exothermic lattice energy? For example, if I have NaCl versus MgCl2, which one do you think is the stronger lattice and why?
Sir, here MgCl2 is higher.
It's got a greater charge,
Exothermic.
right? So
Yeah, because Mg has 2 plus.
so it's going to have a higher lattice energy, I mean, or more exothermic lattice energy. And the reason for that is that Mg not only has a greater charge, which is +2, but it also has a smaller ionic radius as well. Well, when you compare it with compared to Na+1, I mean that's going to be your reasoning. So how did I figure out whether Mg had, I mean the charge is obvious because Mg has greater charge, so it's going to lead to more attraction. So it's going to be a stronger lattice. So how do you determine the size? That's also something from AS. How do you determine the size of the ion? Which one is bigger? Which one is smaller? Na has 11 protons. Mg has 12 protons. The electronic configuration of Na is 281. Of Mg, that's 282. But since they're forming ions, this is +1 and this is +2. So that means they basically have the same number of electrons. So how did I determine that Mg is the one that's smaller in size? Saf, that's what I'm saying, that they have exactly the same number of shells, same electronic configuration. Saf, they both have exactly the same number of shells, the same electronic configuration, but the ions. So how do you determine that Mg is smaller?
So is it because the Mg has +2, so it attracts the electrons more strongly, so the ionic radius decreases?
Basically, it's got more protons in its nucleus, 12 protons. I mean, so they have the same number of electrons, exactly identical electrons, but this has 11 protons and this has 12 protons. So because of the greater protons, the pull or the attraction for the electrons is stronger. So this one has more protons. So that's why it's going to have more attraction for electrons. So just remember, okay, how do you and let's do another one. Let's say I've got oxygen -2 and I've got nitrogen -3. This is 8 protons, this is 7 protons. Which one do you think is the bigger one out of these two? Do they have
Nitrogen.
bigger one? No? Because they have exactly, I mean, this is actually 2 and 6. This is 2 and 5, but this is gaining 2 electrons. So this is actually 8. This is gaining 3 electrons. So this is also 8. So they have the same electrons. Oxygen is going to be the smaller one. Why? Because it's got more protons or more nuclear charge. And this is the one that's going to be the larger one because it's got fewer protons. Okay. So remember this, when you have the same electronic configuration in ions, you can figure out based on the number of protons, who's the bigger one, who's the smaller one. Okay. You clear? Is this thing clear?
Yes, sir.
Yes.
Yes.
I said then there's the obvious case. If an ion has more shells, then it's obviously a bigger one. If the ions has fewer shells, then it's obviously the smaller one. So those are the obvious cases. Like if they tell you to do a comparison between the oxide ion and the sulfide ion, then obviously this is 8 electrons, so it's 2 and 6, but two electrons are gained, so that's 2 and 8. Sulfur is 16 electrons, so that makes it -2 makes it 18 electrons, so that's 2 and 8 and 8. So this is the obvious case. You can just figure out by just writing the electronic configuration. The one that has got more shells, that's obviously the bigger one. So that's so this one is the obvious case. But remember, just a quick revision, how do you figure out which ion is bigger and which one is smaller? Coming back to this. इसका बताओ कि I've got NaCl versus KCl. Like if you know group 1, it's lithium, sodium, potassium, and so on. So which one is the stronger lattice between the two?
KCl.
Stronger? K is the bigger ion, remember that. Bigger ions, they don't form strong lattices. They don't form strong bonds. Bigger ions are like further away. So this is actually the weaker lattice. Okay, ये बात clear? Is this clear?
Yes, sir.
Okay, the charges are identical. So the charge is not really much of a factor here because they've got identical charges. NaCl is the one that's the stronger lattice. So it's going to have the more exothermic. अच्छा एक ना इसका A2 paper करा. I'll give you an idea about the A2 chemistry paper 4. Okay, what happens in A2 chemistry paper 4 is that you get asked almost every question because it's a 2-hour paper. It's a 100-mark paper. So you get asked a lot of questions. I mean, every question, like 9-10 questions, all of them are big questions with many, many parts. So what happens is that almost everything gets asked. It's not like paper 2 in AS. In paper 2 AS, a lot of things don't get asked. I mean, they ask very few things. Like if you prepare for the whole syllabus, so maybe just 3 out of 12 topics, maybe just 3-4 topics are covered. So A2 paper के अंदर क्या होता है कि बस they ask almost everything. ठीक है? So some questions are just always going to be asked. I mean, questions like these, they would always be asked in every paper. So you have to like prepare thoroughly. So almost everything that's written is going to be asked in your exam as well. But anyways, it's a small thing. Just remember how to identify which lattice is strong, which one is weak. And so you either have to look at charge or the ionic radius, or you have to look at both of them. In the case of MgCl2, both of them were the factors. Mg had a greater charge, but it also had a smaller ionic radius as well. So वो दोनों factors आ रहे थे, ठीक है? So you have to determine what the factors are. Is this clear? You clear? Should we move on?
Yes.
Yes.
So now we're going to come to the main thing, which is like, I mean, these are all just like 1-2 mark questions, right? Definitions, etc., factors affecting lattice energy. That's all 1-2 mark questions. Now we're going to come to the big question, which is kind of like the Hess law. I mean, it's exactly like the Hess law. There's a Hess cycle, which is known as the Born-Haber cycle. Now that's going to be your 7-8 mark question. So the Born-Haber cycle, it's basically a Hess cycle. It's the same law. One path is equal to the other path. So you create these paths. Now, what the Born-Haber cycle is, I mean, what is it? It's a very specific application of the Hess cycle, and it's used to find lattice energy. So its specific purpose is you're going to learn how to calculate lattice energy. The thing is, that certain processes cannot be measured directly. I mean, for example, I'm just giving you an example, like if somebody wants to find out the enthalpy change in the laboratory for this particular reaction, can you guess, can somebody be able to calculate it directly or not? Like, it's just simple carbon burning with oxygen to form carbon monoxide. So make a guess, इसमें क्या होगा कि can you find this enthalpy change in the lab directly or not? Any idea? Any idea?
So is it the delta H formation of CO?
No, I'm just saying. My question is that you have to do this reaction in the lab, right? And you have to just calculate the heat energy which is evolved during this reaction. Can you do this in the lab?
So some will be lost.
Let's say there is heat loss. I'm just saying, can you do this reaction in the lab?
Yes, I think so.
There's a big problem over here. You can't actually do this reaction in the lab. The problem is that it's actually very difficult to actually form carbon monoxide, because when you try to do this reaction in the lab, you'll probably end up with carbon dioxide. Do you get my point?
Yes.
So the point is that there's certain reactions that are like very difficult to actually perform in the lab, because you just can't get them right? So what you do is, that's where the Hess law becomes useful, because since you can't really do this reaction in the lab, what you instead do is you burn carbon with oxygen, and what do you get? You're obviously going to get carbon dioxide. That's, if you burn it in excess oxygen, you're going to get carbon dioxide. If you burn this one, carbon monoxide with oxygen, you're also going to get what? Carbon dioxide. That's the only product you're going to get. So you actually go for the indirect method. You burn carbon, form carbon dioxide. You burn carbon monoxide. If you take carbon monoxide, pure carbon monoxide, and then you burn it in oxygen, the only product you're going to get is carbon dioxide. That's it. So you can perform these reactions, this reaction as well in the lab. These can be done. The one that I'm putting across on, that can probably, it's going to be very difficult to actually do in the lab. So what you do is you take the indirect path and you measure the enthalpy change of this reaction. Okay, so do you understand what the purpose of the Hess cycle is? That reactions, it's not just that you're just drawing Hess cycle. It's just that enthalpy changes for some reactions are very difficult to calculate experimentally. Is that point clear?
Yes.
So that's the thing with lattice energy as well, that actually measuring the lattice energy directly by just doing an experiment like this part. I mean, you take gaseous ions and then wait for them to form the ion. I mean, it's kind of like impossible to actually do in the lab. I mean, you can't do that in the lab. So what you do is you measure it indirectly. So that's where the Hess cycle is useful. I said, now the Born-Haber cycle is normally a very, very typical. I mean, they do come up with some variations, but normally it's just a typical Hess cycle, which starts off like this, that remember, you have to find the lattice energy, and it's specific to ionic compounds. Lattice energy is specific to so you can start a Hess cycle from any point. Okay? The easiest point to start off with is enthalpy of formation. So let's go with aluminium. Let's do a simple one. Let's go with MgCl2. So what is the enthalpy of formation of MgCl2? It's elements Mg and Cl2. So Mg is a solid, Cl2 is a gas. And Mg and Cl2 elements, they react to form 1 mole of MgCl2, which is a solid. ठीक है, तो ये that's your enthalpy of formation. then you go for the alternate path. So that's the whole process. You take the elements, you react them together, you form MgCl2, you measure this value. And then there's an indirect path. So there would be lots of steps when Mg and Cl2 react together to form MgCl2. A lot of steps would be happening. Now, the first step would be that you would have to atomize the elements, which means that Mg right now is metallic Mg. So first you would have to break the metallic bonds. So when you break the metallic bonds, what do you get? You get magnesium gaseous atoms. So that's basically your enthalpy change of atomization of Mg. ठीक है, हमने पढ़ा था Mg atomization. Element turns into gaseous atom. So basically you've broken the metallic bonds of Mg. You've got Cl2 over here. The Cl atoms are bonded together. So you can break the bonds and you'll get what? 2 Cl gaseous atoms. So what is that? That's the enthalpy of atomization of Cl times 2. Because you're forming 2 gaseous atoms. And this one is basically equal to the bond energy because you're just breaking a Cl bond. ठीक है, ये बात clear है ये वाली? Is this clear, the first part?
Yes.
Yes.
So the first part, remember, my focus is to form the ionic lattice, MgCl2. So I first need the atoms. I don't need the elements. I want the atoms. What is the next step? Once I have the atoms, I want to turn them into ions. So the next step is that I need to ionize Mg and I need to form Mg2 plus gaseous ions. At the same time, I need to ionize the Cl atoms as well. I need 2 Cl negative ions, gaseous state. So I'm basically ionizing the atoms now that I've formed. So it's the first plus second ionization energy of magnesium. And the Cl is actually turning into Cl minus 1. So it's gaining electrons. So that's the electron affinity of Cl. And it's times 2 as well because I've got 2 Cls. ठीक है, तो ये clear है, हमने अभी पढ़ा था कि Mg has to be ionized and Cl has to be gaining electrons. That's electron affinity. Is this clear?
Yes.
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 And finally, you've got the last step, which is gaseous ions forming the ionic lattice. The gaseous ions will get together and they'll form the ionic lattice, and that's your lattice energy. Okay, this one is your. So your cycle is complete. Basically, what you have to do is you've got to atomize, you've got to ionize. ये मैं highlight कर लेता हूँ, ठीक है? So you need to atomize the elements first, turn them into atoms, then turn them into ions. And once they turn into ions, then you just form the lattice by putting the ions together. So enthalpy of formation is basically equal to all of this. And that's basically your Born-Haber cycle. For any ionic compound, you can construct a Born-Haber cycle like this for any ionic compound. But the only thing is, a lot of times this Born-Haber cycle is actually kind of, so it's kind of drawn like this with the energy axis. You can throw away again. So now, in a lot of cases, the Born-Haber cycle is drawn with an energy axis. I mean, the same cycle, the one that's over here. The only thing is that it's now enthalpy of formation. Most of the time, it's it could be endo, it could be exo, but most of the time for ionic compounds, it is actually exothermic. So Exo means if there's an energy arrow over here, exo means going downwards. If you go downwards, you're losing energy. If you go upwards, you're gaining energy. So you have to just draw the same cycle, but you have to keep this in mind. Like, what is the direction of the arrows? So starting with enthalpy of formation. Enthalpy of formation is what? It's mg plus Cl2 and since enthalpy of formation is exothermic, it's forming 1 mole of MgCl2 solid. So that's my delta HF. That's the first thing. Remember, I'm drawing the same cycle. Then I have to, what do I need to do? I need to atomize the elements. Atomization is you're breaking bonds. So that's endothermic. So the arrow needs to go upwards. So the arrow is going to point. It's going to point upwards. It's still pointing downwards. So the arrow has to go upwards. And it's going to go upwards. So this is the step where I atomize. I'm going to atomize Mg. Gaseous. I'm going to keep Cl2 as it is in the first step. In the next step, the Mg has been atomized. It's gaseous. Now the Cl has also been atomized. So this is enthalpy change of atomization of Mg. And that's the enthalpy change of atomization. Bas ye draw karke na we'll finish this. So that's the enthalpy change of atomization of Cl. Remember, I started off at this point. This point is this point. Formation was negative, so it went downwards, and atomization was endothermic, so you went upwards from here. You just followed the direction of the energy. You had to atomize Mg and you had to atomize Cl. Normally, you don't do it in one step. You actually take two steps. You turn Mg into gaseous Mg in the first step, then you take the Cl2 and turn it into gaseous Cl. That's the second step. ठीक है उसके बाद क्या करना है once you atomize that you ionize so ionization is endothermic as well so ionization is I'm going to take this arrow ionization is endothermic so the arrow has to go upwards so it's going to turn into what Mg2 plus Mg is going to lose 2 electrons the Cl at the moment is not gaining electrons so Cl as it is so that's the first plus second ionization energy of Mg. अच्छा ये सारे follow कर रहे हो ना कि is this clear? This thing. Ahmed Saad. Ahmed.
Yes.
अच्छा then when Mg loses those 2 electrons then it's Cl that gains electrons right so it becomes Cl minus 1. Now electron affinity the first one that is exothermic so arrow jo hoga na that's going to go downwards from this point. So the arrow is this go ठीक है. So now the arrow goes downwards. Why? Because Mg has already been ionized. That was endothermic. Cl is the one that's going to gain electrons, and that's your. So this arrow over here is the electron affinity of Cl, and this is. So ये वाला ना this is times 2. Okay, so this one. So this one over here is times 2. Or finally, the last step is you got gaseous signs. So they're going to form the lattice. I mean, this one is a lot easier compared to this one. Okay, this one, drawing this one according to the energy axis, that's slightly time consuming. So finally, your gaseous ions are forming your, and that's your lattice energy. Okay. So it's kind of exactly the same process where we started off at this point, which is elements. The elements are turned into atoms. The atoms are then turned into ions, Mg2 plus. Then the Cl gains electrons, become Cl minus 1. Then once you get gaseous ions, you form the ionic lattice, and that's it. So your cycle is complete, and this is drawn according to the energy axis, this side. Okay, you clear? Is this clear, this one?
Yes.
Yes, sir.
Yes.
So there's a times 2 at the delta H atomization of Cl.
ठीक है, that is times 2. अच्छा, इसके अंदर ना the सबसे जो बड़ा मसला है ना, the biggest problem, that is you have to get every value correct. Because applying the Hess law is easy. ठीक है, we're going to do a lot of questions and we're going to practice a lot. Once you have the Hess cycle, then doing the rest of the stuff is easy. But there's going to be a lot of addition and subtraction. And I mean, for example, what is the Hess law? Hess law is that one path is what? Equal to the other path, right? So delta HF is basically equal to all of this stuff. And if lattice energy is missing, you should be able to make an equation. You should be able to find that out. So yahan pe na, that's exactly what you're going to do. You would have to sketch it. You would have to learn to sketch it. You have to get every single small thing correct, because if you had missed this 2 over here, then your answer would obviously be incorrect. Similarly, if you had missed this multiplication by 2, so you have to get everything right. How many Cls are gaining electrons? That's 2 of them, so that's multiplied by 2. So you have to get everything exactly right. So iski phir practice we'll do. I mean, most of the questions would be around this. So we'll be making a lot of Hess cycles, and तो फिर next class में करते हैं, ठीक है? और उसके अंदर ना फिर so basically we're done with this. We'll just practice a lot of past paper questions, drawing the same stuff. ठीक है? Clear है?
Yes.
Yes.
तो ठीक है, फिर next class में ना we'll just practice more questions, a lot of questions on this, ठीक है? तो चलो ठीक है, let's talk on आज क्या Thursday?
Yeah, Thursday, yes, sir.
Thursday, ठीक है. So let's talk on Monday then, ठीक है?
Oh,
Sir, could you send this board link to the group, sir?
It says board link, man. You should just one second. Let me see how this is shared. Well, you would have to give me your email. Yeah, this is OneNote, I think. This is OneNote. So you would have to give me. I'll check if I can do that, but send me your email, okay? Just put it in the group, okay? I'll add it here. I mean, you have it actually.
Yes,
It's
sir.
मैं तुम्हारे पास तो है.
Yes, sir. Yes, sir.
बस ठीक
Should
है.
I send it there?
नहीं ठीक है, वो email बस मुझे ना send me on WhatsApp, ठीक है?
Okay, sir.
चले ठीक है. Okay, ठीक है, अल्लाह हाफिज़.
Allah.